Hello all. In the previous lectures, we discussed the basic concepts of RCC design and the methods of design. In today's lecture, we will study a key topic known as the types of RCC structure. And this classification is based on amount of reinforcement provided in a reinforced concrete member, especially in flexural members such as beams and slabs. Understanding the types of section is essential because it helps us to predict the mode of failure as well as to ensure ductile behavior. In addition, we can also design safe and economical RCC members. In RCC flexural members, both concrete and steel resist bending moments. Let us consider a rectangular reinforced concrete beam having a width B and an overall depth D. Now assume that this beam is simply supported and is subjected to transverse loads such as uniformly distributed load or point loads. Due to the bending action, the beam undergoes curvature. Because of this bending, the top fibers of the beam are subjected to compression and the bottom fibers of the beam are subjected to tension. Since concrete is weak in tension, it is not relied upon to resist tensile stresses. Therefore, we provide steel reinforcement in the tension zone that is near to the bottom of the beam. The area of this tensile reinforcement is denoted as AST. Now let us define an important geometric parameter. So the distance measured from the topmost compressive fiber of the beam to the center of the tensile reinforcement is known as the effective depth and it is denoted by small d. This effective depth plays a crucial role in determining the moment carrying capacity of the beam. Next, within the beam cross section, there exists an imaginary line that separates the compression zone from the tension zone, which is shown in a red color. And this line is called the neutral axis. So at the neutral axis, the strain is 0. And hence, the stress is also 0. Above the neutral axis, the concrete is in compression and below it, the material is in tension. Now let us discuss the stress distribution. Under the working stress method, we make a fundamental assumption that both concrete and steel behave as linearly elastic materials within the working load range. Because of this assumption, stress is directly proportional to strain as well as the stress distribution across the depth of the beam becomes linear. As a result, the stress distribution curve across the beam section is represented as either a rectangular or a linear shape as shown in the figure. This linear stress distribution is one of the key assumptions of the working stress method and forms the basis for analysis and design using permissible stresses. So depending on the percentage of steel provided, RCC sections are classified into 3 types. One is the balanced section, in which the actual depth of neutral axis will coincide with the critical depth of neutral axis. Second one is under reinforced section, in which the depth of neutral axis, neutral axis is less than the critical depth of neutral axis, which can be seen from the second figure, the stress distribution curve, in which XA is less than XC, where XA is the actual depth of neutral axis and XC is the critical depth of neutral axis. And finally, the over reinforced section, in which the depth of neutral axis will be greater than the depth of critical neutral axis. or otherwise mathematically XA is greater than XC. So in under reinforced section, the neutral axis, the actual neutral axis will pass towards the compression side. Whereas in the over reinforced section, the actual neutral axis will begin to move towards the tension side. So each type of section behaves differently under load and has a different failure pattern. Now let us discuss the balanced section. In the balanced section, the amount of steel provided is exactly equal to the balanced steel. So steel reaches yield stress at the same time concrete reaches its maximum compressive strain. So both steel yielding and concrete crushing occurs simultaneously, which is a theoretical concept. In practice, this may not be possible. So this section represents the theoretical limiting condition between under reinforced and over reinforced sections. So the failure of a balanced section is sudden with very little warning. So although the section is efficient in terms of material usage, it is not preferred in practice because it does not provide sufficient ductility. Hence, balanced sections are mainly used as a reference condition for design purposes. Next is the under reinforced section. In an under reinforced section, the amount of tensile reinforcement provided is less than the reinforcement required for a balanced section. So when the load is increased, steel reaches its yield stress first, and the concrete is still within its compressive capacity. So this results in a large deflection, visible cracking, as well as warning before failure. Hence, failure is ductile and gradual. So in an under reinforced section, the steel yields first and the concrete crushes later. So this type of failure is desirable because it gives sufficient warning before collapse. Due to its ductile nature, IS 456 recommends designing RCC beams as under reinforced sections. So this ensures safety and better performance during unexpected overloads or earthquakes. So finally, we consider the over reinforced section. In an over reinforced section, the amount of steel provided is more than required for a balanced section. So when the load increases, the concrete reaches its crushing strain first and the steel does not yield at this stage. So this results in a sudden and brittle failure. Over reinforced sections fail due to crushing of concrete in compression. So this type of failure occurs without any warning, making it dangerous. Because of this brittle material, over reinforced sections are not permitted in RCC design. So IS codes restrict the maximum percentage of steel. So this ensures that the section remains under reinforced. Now let us compare the three types of sections. So under reinforced section will result in ductile failure wherein the steel yields first, which are preferred in design. In case of balanced section, simultaneous failure of steel and concrete will occur, which is a theoretical case. On the other hand, in over reinforced section, there is a formation of brittle failure in which the concrete crushes first, which is not allowed in practice. So this comparison clearly shows why under reinforced sections are recommended. To conclude today's lecture, RCC sections are classified based on the percentage of steel. Balanced sections represents a limiting condition. Under reinforced sections provide ductility and warning before failure, whereas over-reinforced sections fail suddenly and are unsafe. Therefore, in practical RCC design, we always aim to design under-reinforced sections. Thank you.